Good afternoon, everyone, and thank you for joining this NMRG session. So I'm Jean-François. I'm co-chair of this research group with Jefferson Campos Nobre. So this is first session of NMRG. So first, a note regarding intellectual property. The NMRG is a research group from IETF. IETF follows the IETF intellectual property right disclosure rule. So as you can read here, but you have also the RFCs that you can consult, and the link that in particular, if something that you present or discuss is covered by patent or patent application, you should disclose it in a timely manner. Also, you have to know this point. In particular, the IETF routinely makes recording of online and in-person meetings, including audio, video, and photographs, and publishes those recording online. So if you participate in person and choose to not wear a red do not photograph lanyard, then you consent to appear in such proceedings. And if you speak at a microphone, appear on a panel, or carry out an official duty as member of IETF leadership, then you consent to appearing in a recording of you at that time. Also, if you participate online and turn on your camera and all microphones, then you consent to appear in such recordings. Regarding the privacy code of conduct, so again, here are important points that you have to read and also reference to the different documents. So beyond what has been said regarding the recording, it's important that personal information that you provide to IETF will be handled in accordance with privacy policies that is mentioned here. And as a participant or attendee, you agree to work respectfully with other participants. And please contact the Ombuds team if you have questions or concern about this. So also as an NMRG's research group, it's important to remind you the goal of the IETF that is different from the IETF. So IETF focuses on longer-term research issues related to the internet, while the parallel organizations, the IETF, focuses on shorter-term issues of engineering and standards making. So IETF conducts research, it's not a standard development organization. So while the IETF can publish informational or experimental documents in the RFC series, its primary goal is to promote development of research collaboration and teamwork in exploring research issues related to internet protocols, application architecture, and technology. And we also reference here the RFC 7418 about an IETF primer for IETF participants. So here are the useful links for today. So please also feel free to help us, Jefferson and I, to take notes if we think we do not catch something properly in the notes. And I will not talk too much because, as you probably have seen in the agenda for today, in the next session, it's quite a dense agenda. So here I just list the presentation of today. So as you can see, most of presentation is related to AI, but the last one will be also related to the NMRG draft about use case of intent-based networking. I just want to highlight there will be another session this week in IETF on Thursday, and what is not mentioned in the slide, but it's also important is that you may have seen the announcement on the mailing list that we have an interim meeting on Saturday that is a joint session with ZSM. That will be also held here. So after this quick introduction, I think we can start with the first speaker. So I invite Wen Longding for the first presentation about towards intelligent network configuration management with LLM.
Hello.
Where is the slide?
So I get started. Hello, everyone. I'm Wenlu Ding from the Chinese University of Hong Kong, and I'm a PhD student supervised by Henry Hongxu. And today I'm very glad to share our works about using LLM to uh, uh, manage a large set of the network configuration management tasks. So okay. To begin with this topic, we first like to say that configuration management is really complex since there are three aspects. The first is there are many large-scale devices, and we can see that there are 1 million devices for each typical DC regions with more than 70 DC regions in the large network, and there are more than 1,000 devices for the WAN. And the second is that there are many huge number of configuration lines, such as first that for a typical device, the configuration lines exceed 1 million lines, and there are many protocols such as Echo, BGP, IGP, and some other components such as roadmap, interface, and authorization configurations. So the third one is that the configuration will update really frequently, and from a large production network, we found that there are over 100 manual updates every week, and this includes many aspects such as the new devices prefixes and new policies groups extra. So that we give a conclusion that the operators need many automated tools here. So here we show that there are three aspects of our in our tool suite. The first is understanding the existing network. It receives the query network flows and output the flow intents in the existing works. And the second is the new configs intents. And we input this to perform the intent-based configuration. And its output is the new device configuration scripts. And the third task is about the configuration verification, and its input is about properties to be verified and output the final script that is verified for deployment. Okay, so the first work is about understanding the existing configuration, which we aim to in search of the lost time, which is the intent recovery in the network configurations. So the key problem here is that given an observed network state of interest and infer why it exists with the evidence, such as we ask a flow about why can a prefix reach another prefix on a certain port. And our intent recovery asks why the property holds instead of the verification task that ask whether the property holds, or the specification mining task that ask what the property holds. And there are three rationales behind this topic. The first is why the problem exists. It is about because of the evolution of existing configuration is lossy due to the context decay. The second is why the work is hard. It is because that this task is ill-suited with inherent ambiguity, such as the configuration for the intent are distributed across the devices and times. The third that is why this topic deserves solving. It is because the recovered intents enable safe and subsequent intent-based networking tasks. And okay, so our key insight behind this is that we find that the snapshot alone is undeterminist, but the original design leaves the residual traces in the surrounding artifacts. So our insight here is to use some meaningful context as the regularization. So what is the useful traces and how to mine the context? And we find the first useful context is about semantics, and the data source is about IPAM, which is a mapping table, which maps the prefix or the entities to its names, tags, or the hierarchy relations. And the challenge behind using this context is about the search space exploration, which is the many-to-one entity mapping. And second is about the provenance. which data source is a configuration snapshot. And the challenge behind this is the reverse tracing, that is the distributed configuration across device for a typical certain flow intent. And the next, the three contexts is about history. Its data source is from the Git evolution, and the challenge here is about shadowing detection, which is the configuration of the different intents override each other. Okay, so we developed three engines to resolve these three challenges. The first is about a semantic engine, which we build a semantic context forest and used unrelated tag plumbing to get some multiple level semantic candidates. For example, if we ask about the prefix about 10.0.2.8 here, and we can get all its tags and meaningful metadata tags here. And the second is about the provenance engine, which we first get all the configuration on the traceroute devices. For example, we use the traceroute between two prefixes, and we get all the configurations on this traceroute. And then we use LM to perform the affinity-based filtering for these intent flows, and finally get the most contributing configuration lines here. And the third is about the temporal engine, and here is to our key idea is to replay the Git history and compare each other and use LM to analysis which is the most related to intent flow and current state. And then we get a timeline of the related rules. Okay. Okay, so our key idea here, or the primary design, is to use a deterministic heuristic pipeline that progressively applies each context dimension as filters here. And our solution here says that this full pipeline achieves 71% exact match accuracy and 79% intent F1 score here. And there are some future works to further optimize this, which we can build a joint optimization framework as the context in the three dimensions are intertwined. And the second task is to conduct intent-based configuration, and we use echo and or the access control list as an example. Okay, so you can see that for the common manual configuration, operator needs to infer the policy or the intent to the attribute specifics and then deploy and verification through a huge loop. And so there are some automation challenges here about the intent configuration reasoning, which there are some complex syntax and network specific in the low layer configurations. And the conflicts with existing rules, such as numerals and intertwined existing rules, are very complex to solve. And the last one is about optimizing the deployment, because naive method deploy the redundant rules. So we use three modules to solve this. And the first is that there should be okay. Yeah. So okay. There are two major challenges within this module. The first is that LM is prone to hallucination, so we build a echo intermediate representation templates with some well-designed prompts, such as the chain of thought reasoning. And to resolve this. And the second is that LM lacks of the network-specific information, such as the gateway and interfaces as prefixes. So we prompt LM with the and semantic network mapping table, which provides the network-specific information that LLM lacks here. So that we can see that using this, LLM can translate natural language intent into the echo rules and the deployment gateway information here. And the second is that if we use for the conflict detection, if we use the simple ways to such as checking the overlapping and the opposite actions here, there are some false positive cases. The first is that because of there are some false positive because of the preceding rules, and second is that some identified conflicts are not on the target interface. So we use two modules. The first is the true match flow space conflict detection, and second is the interface path validation to resolve these two positives. And after we get all the conflicts, we ask LLM to ask operators to propose the subset of conflict flows and to preserve the existing rule that should maintain the old actions that we said it is the resolution with operators of the protect mechanism. And here that for the deployment, we also develop some, compared to the naive endpoint deployment method, which deploys the rules at the gateways, we also have some novel observations to reduce this total deployment rules. And we finally use a joint optimization formulation to formulate these observations. And as a result, we can see that for these three modules, it can have some low latency and have some further accuracy, detection accuracy, or and the deployment accuracy than before. And the last is about the configuration verification. And the key question behind is that the current formal tools such as Batfish servers from low speed and high memory, but in the large networks, there are strict timeline lists and the large cloud network scales. So the formal verification tools such as Batfish cannot scale to these network requirements. So that we can see that, so we opt to the selective verification and we only use partial tools with the configuration for the formal verification. But we can see that in this example, if we select the shortest path, here we will select the wrong routers to analysis and finally unable to identify the key reasons that you identify the failure of this reachability. So that we can see that our conclusion is that naive or heuristic selection is error-prone without knowing the holistic configuration or the routine situation across the entire network. So our key idea is to use the LLM-based network analysis to infer the routine states before and after configuration changes and identify the affected routers across the entire network. So the rationale behind is that this approach offers high confidence than heuristics, as LLM can rapidly reason about across protocols. And it is much more confident than what humans do. So that we mainly do two evaluations. The first is about the naive prompting, that we prompt all the configuration and topology information to the LLMs with detailed instructions. And second is use agent, that we provide LLM with some tools to extract configuration and topology and design docs. And we can see that for the task completion time and accuracy, the naive prompting configuration or topology information still suffers from scalability issues due to the context window, but the agent can have better scalability than the Batfish. And the second is that for the accuracy, and we can see that for the agent mode, its accuracy is very high. So that's our conclusion is to let LLM play more and analysis less through the agent mode that can better unlocks its potential. Okay. So that's all for this speaking. And our next step is to do some more detailed implementations and evaluate on some real productions networks and seek for some opportunities for real deployment. So thank you. I'm free to take your questions.
Thank you. So we have time for one quick question.
Yeah, quick questions. Very nice talk. So I wonder how much time can this system saved for the human operators? Like, did you taste or evaluate? Thank you.
So for the first and the third topic, that because of network scale is very large, the human typically cannot analyze the whole network. So that is human infeasible. So we make it the holistic analysis within some hours or minutes. And for the second intent-based network configuration task, we have compared with the state-of-art work, we can have 20 times faster than the current intent-based networks works. So thank you.
Okay, thank you very much. Thank you. So let's move to the second talk that will be given by Abdelkader Mekraj, and he is online. So just, Abdelkader, let me just prepare the slide, and I will give you the control of the slide then.
Let me enjoy the opportunity and ask for the people in the room to log in to on-site too, because we need this login in order to count the number of participants. Thank you.
Hello, everyone. Do you hear me well?
Yes, we can hear you very well. And normally you should have the control of the slide now. So
Yes,
please,
yeah, I have it. Thanks a lot. So my name is Abdelkader Mekraj. I'm a researcher at Eurocom. I'm very glad to be here today and would like to thank the chairs for inviting me to this NMRG meeting. So in today's presentation, I will talk about our approaches on agentic AI for the intent-based networking concept. So basically in this presentation, I will start with presenting the intent-based networking concept. Then I will move to our two approaches using agentic AI and also, of course, large language models in intent-based networking. So I'll start with intent translation and then intent assurance and finish with a conclusion. So let's start with IBN. Basically, in cellular networks, we have what we call the infrastructure layer that will ensure the connectivity between the UEs and some 5G network or private network. So this infrastructure is composed of different technological domains. The first one is the radio access network to ensure wireless connectivity between the UEs and the G-Node V. Then we have the core network to ensure authentication, session management, etc. And we have finally some vertical applications deployed at the edge or cloud. So this is the infrastructure. And to manage this infrastructure and the resources, the users need to communicate with a management layer. And we call it here the OSS, Operations Support System. Basically, in traditional network management, frameworks rely on low-level technology-specific configurations, which is error-prone and poorly suited for autonomous networks like beyond 5G networks or 6G networks. To tackle this, standardization and research are pushing towards the use of this new concept called intent-based networking, which will simplify network management and enable the evolution towards autonomous networks. So in this concept, the users will use their intentions, or what we call here intents, to manage the network. And these intents abstract the complexities by allowing users to express what they want rather than how to implement it. It also supports closed-loop control, which allows system to adapt continuously to service objectives without any human intervention. So IBN is composed of different stages. The first one is intent reporting, where the users will declare the intent using a declarative structure. Then we have intent translation, where the high-level intents will be translated to low-level configurations, and then these low-level configurations will be activated in the intents activation phase. Then we have intents assurance, which is basically a closed loop that will ensure the intents respect the specified requirements. And finally, we have intents reporting to provide feedback to the users about the status of their intentions or intents. Actually, in current IBN, we have different standardization institutions that are defining the way users communicate with the OSS. We can mention 3GPP, TM4UM, and ETSI. And all these standardizations bodies, they are defining OSS API endpoints and JSON structures. So in order to communicate with this OSS, the users need to use API endpoints and create these JSON structures. You can see an example of this JSON structure on the left side. This is called the NSD, Network Service Descriptor, from ETSI. And users need to generate this in order to define their intents. The challenge here is that the users must understand these APIs, which complicates IBN adoption. In our approaches, we want to move towards the use of natural language to define the intent, which is the simplest form of intent. Basically, this will remove the API complexity. It will allow users to manage network without any prior knowledge. And also, it will enable more automated and scalable intent-based networking. So in this setup, the users can use natural language in order to define their intents and send them to the OSS, to the management layer. And also, the network can provide feedback to the users in natural language. Of course, here we need an AI approach that can understand and generate this natural language text, where LLMs, in this case, are the best candidates. Now let's move to intent translation with LLMs. As I said, here in this intent profiling phase, in current IBN, the users are using API endpoints to define their intentions. You can see here an example of the OSS from Eurocom. We have our operation support system, and this is the set of API that the users have to use to manage the network. On the left side, you can see the set of API endpoints. We have different API endpoints to manage the infrastructure, to manage the services, etc. And you can see on the right side, one API endpoint, which is service create. So if the users want to deploy a service on our infrastructure, they need to call this endpoint, and they need to generate this JSON, which is called the NSD. So this is the current intent structure. So OSS APIs have many endpoints, each for different functionalities. So we have endpoints for managing infrastructure, for managing resources, and also endpoints for managing services. The problem here is that each endpoints have a diverse JSON structure depending on the standards. So 3GPP, TM4UM, ETSI are defining different JSON structures. And this, of course, complicates IBN adoption because users need to understand these endpoints and need to understand how to create their JSON bodies in order to use this IBN system. That's why we want to use natural language to express intents, and then we will perform translation to low-level configurations with an LLM-powered approach. This is an example of an intent in this setup. The user can say, deploy a 5G communication service on the most available parts of the virtualized infrastructure in natural language. And actually, this intent will be translated to 3 API calls in our OSS. So the first one is get VIMs to retrieve all the infrastructure. Then post resource availability to check the availability of each infrastructure. Finally, post service create to create the service. And before creating the service, the users need to create this JSON structure. So in this work, we need an AI approach that can move from natural language intents to a set of API calls, a workflow of API calls with the appropriate JSON for each API endpoint, and then execute these API calls to fulfill the intent. So this is the task that we want to do with the LLM. But of course, this set of tasks is very complex for one LLM agent to handle. And therefore, this is why in this approach, we are using multiple LLM agents under the umbrella of agentic AI to fulfill the intent, each responsible for a specific role. This is why we introduced this framework called OSS-GPT, short for Operation Support System GPT, which basically translates natural language to a set of API calls, generate their JSON, and execute them sequentially to fulfill the intent. You can see the design of OSS-GPT here in this figure. It is between the users and the OSS. And basically, it is composed of 4 main agents. So the first one is the assistant agents. This one will interact with the users using natural language. And so this assistant can respond to generic questions to the users. But if the user asks questions on how to manage to manage the infrastructure, then this assistant will forward the requests or intent to the planner. The planner will set the set of API calls to fulfill the intents. So it will choose which API calls and in which order. Then it will request the executor to execute each API endpoints based on some tools. And finally, we have the reporter agent that will see the conversation history and report back the feedback to the users in natural language. So we are using here, as you can see, 4 main agents that are working collaboratively in order to fulfill the natural language intents. All these agents are trained using in-context learning. So we are using a generic large language model, and we are training them using prompt engineering techniques. However, we have another LLM here. The executor is executing API calls using some tools. And before executing the API call, this executor needs to generate the JSON structure. In our case, we have the NSD, Network Service Descriptor. So for this, we created this tool called Blueprint Generator, which is an LLM that will generate NSDs from natural language. In this case, we developed this LLM using a fine-tuning technique, and we call this the NSD expert. So let's see more in details on how we created this small language model. The task was to generate NSDs from natural language. So the first challenge was how to create the dataset. Since no public datasets available in the state of the art, we built our datasets from scratch. So we started with 100 high-quality intent NSD pairs, and then we augmented this dataset using LLMs in context learning. And then we fine-tuned an existing LLM with the LoRa technique. So LoRa is a parameter-efficient fine-tuning that allowed us to inject this NSD expertise of an existing open-source LLM. For implementation details, we are using 2 machines. The first one is on the bottom one. It's a Kubernetes cluster, which will host the infrastructure components. You can see here we have the radio access network, core network, and edge deployed. So we are using the 5G stack from OpenAir interface. Then a second machine that will host the management components. So it will host the OSS components. Here we adopt a microservice architecture in our OSS. And then also we deploy in the same machine OSS-GPT. And OSS-GPT is using 2 main LLMs. So GPT-4 for the main agents, assistant, planner, executor, and reporter. And it is using also the NSD experts, which is the LLM that we created responsible for generating NSDs. And we used Olama to deploy this LLM. Of course, this is inference, but for training, this NSD experts was trained using an NVIDIA A100 GPU. We use Llama 3.2, 3 billion instruct open source LLM as the base model. And then we trained it with the LoRa technique using the Ensloth framework. Okay, let's move to the demo now. We consider in this demo that we have 3 infrastructures in the Eurocom testbed, so 3 clusters. And the user, a random user, will deploy 1 radio access network subservice, 1 application on the second infrastructure. So for the terminology, in what we will see in the demo, when we say service, we mean an end-to-end service that can be composed of different subservices. So we can have radio access network subservice, core network subservice, and application subservice. And each of these subservices will be deployed on an infrastructure, and we call it Vim here. You can see here the front end of our OSS. The users have this nice dashboard, and then from this front end, the users can manage infrastructures, the set of clusters, and also services. So for example, here, this random user have access to 3 infrastructures. He can deploy services on these infrastructures. And then you can see, for example, that we have 2 services deployed. The first one is, for example, it is composed of a radio access network subservice and a core network subservice. As you can see here, the core network is deployed on the second Vim, Vim 2, and the radio access network is deployed on Vim 3. Now at this step, let's see how this user will use OSS GPT in order to deploy his intent. So this is OSS GPT interface. This is a debugging interface. Of course, we have a UI that the users will use, but this is a debugging interface where we can see the set of agents and the communication between these agents. So the user introduced this natural language intent. This is an example. Create a new service with name demo service containing 1 radio access network subservice. And this latter contains 1 KPMX app using, and he can introduce, of course, some configuration parameters. And then this should be deployed on the second Vim. So this is the intent, and then OSS GPT will translate this intent to multiple OSS API calls and execute each one sequentially. And at the end, the OSS GPT will generate these reports in natural language. You can see that this report confirms the creation of this requested new service. These are the sets of logs from the OSS that OSS GPT took. So in order to fulfill the user's intent, OSS GPT made all these API calls. So first, it's called the OSS to get the list of VIMs, then post service create to create the service, then check if the service is created, then check if the NSD exists. If not, it requested the NSD expert, and so on. In the front end, you can see that this demo service now is created, which contains 1 radio access network subservice. And it is deployed on the second Vim, as the user mentioned. It also contains this KPMX app, as the user mentioned, and it is instantiated and running successfully. So we've seen how the users use this OSS GPT to introduce intents and deploy their services or activate their intents. After deployments, we have the intent assurance phase. So in the intent assurance phase, it will be a closed control loop at the infrastructure that will ensure intents respect the specified requirements. We have another term for this intent assurance, which is zero-touch network and service management. And it is composed of 3 steps. So the first one is detect or predict anomalies, then identify the root cause of the anomalies within the intent, and then resolve these anomalies to ensure the intent respects the specified requirement. For anomaly detection and prediction, we have a lot of AI methods that have been widely used in research. The problem here is that these AI are black boxes, which lacks explainability, making it difficult to extract the root cause of the anomaly. That's why we have XAI methods, explainable AI methods in the state of the art to explain these AI decisions, and therefore we can extract the root cause of the anomaly. But the problem here is that in the report, in the intent reporting, these XAI values are difficult to understand from users with little domain knowledge. And this removes trust in the IBM system. That's why in this approach, we want to generate these reports in natural language. Our pipeline includes 3 steps. We use AI for anomaly detection and prediction, XAI to extract the root cause of the anomaly, and then we use an LLM agent that will generate this report in natural language to explain the anomalies and then resolve them autonomously. This is the general pipeline of the intent assurance. In this demo, we are tackling one use case of one application deployed at the infrastructure that contains some latency requirements. We are using XGBoost as the AI to predict latency violations, SHAP as the XAI to identify the root cause, whether it's CPU resources or RAM or both, and then Llama 2 to explain the anomaly and resolve it without human intervention. Of course, we are training them using in context learning as well. So we are using a generic LLM, which is Llama 2 in this case. So let's move to the demo. We have an initial allocation of 250 milli CPUs and 250 megabytes of RAM for this application. We are using Grafana and Prometheus for the monitoring to visualize resources. We are using Apache Benchmark to stress the application with a load of HTTP requests, and then we monitor CPU, RAM usage and limits, and also the LLM's output. You can see here the Grafana dashboard of this application with the CPU and RAM usage and limits. And you can see on the right side the allocation, the initial allocation. And then at this step, we use Apache Benchmark to stress the application with a lot of HTTP load. So it will consume more and more resources in terms of CPU and RAM. At this step, you can see that on the bottom, XGBoost, which is the AI, predicted an SLA latency violation. So we give this prediction to the XAI and LLM. And here you can see the outputs or the reports from the LLM based on XAI values, of course. The LLM said that the root cause of the anomaly was insufficient CPU and RAM resources. And to mitigate this, you need to update the CPU and RAM resources to this new value. So we take these new values and we apply them autonomously to update the allocation of this application. You can see here that this new allocation was applied in both CPU and RAM. Then we do this again, and you can see here that XGBoost predicted also SLA violation, but this case, the root cause was only insufficient CPU resources, and this is, of course, from the XAI output. And the solution was increasing CPU to this value. And then you can see here that the new allocation was applied without human intervention. Okay, let's move to the conclusion. You can see here in this figure that this was happened in the demo, in the 2 demos. So this is from the first demo where the users deployed or activated an intent in natural language. And then we've seen how the intent assurance phase works. These are the stages of the IBN intents profiling and reporting are done in natural language, and then everything else was done using the LLM agents. So the advantage here, of course, that's instead of for the users to use the APIs and generate NSDs, they use natural language to manage the network, and this is very simple and straightforward. You can see links here. We have papers and demo on YouTube for if you are interested in more details. With that said, I'd like to thank you very much for your attention.
Thank you, Abdelkader, and we have a number of questions.
Hi, thank you for the presentation. I have some questions related to your metrics and actually the security of your approach. For the metrics, have you considered the 78% availability that the models might deliver as a top because of the agents, right? They will have like the hallucination and they will be the stacks of failure that for for example, for network, we usually don't consider a good resolution when it's not close to 99% of time. So how are you tackling the hallucination, actually the problem solving of the security part onto the studies that you did for your intents and your prompt development? How are you tackling this?
Yeah, so thanks a lot for the interesting question. Security was not the focus, but we are tackling this, for example, with some validation agents. So, for example, here in the executor agents, it will generate this NSD, and therefore, when generating this NSD, we will validate it with a script using Python to validate semantic correction or correctness of this JSON and also the structure. And then also, we are using human in the loop for now. You can see here a tool called human validation. So this human validation will validate the executor actions, the critical ones, in terms if the executor action decided to delete something, called the delete endpoints or put. So we are using humans in the loop here.
Okay, so you're not totally autonomous as it is on the drawing. I wanted to ask you, are you planning to be totally autonomous, and how are you planning to tackle the autonomous play into being able to do anything that the agent might understand into the network, right?
Yes, actually, we did some evaluation in enabling this autonomous 100%, and the results was that for complex intents, like if the user introduced this complex intent that require lots of API calls or lots of reasoning from the LLM, then we have approximately 80% of accuracy. So we are not in the 99%. We have a research paper on it, but I think that's here we need to use more advanced LLMs in the reasoning part so that they will not hallucinate. We also need to include some advanced validation agents, Python, to remove this human validation. So we did some evaluation here. I invite you to see the paper. It is called OSGPT. And we published the results in this paper.
Thank you.
Thanks a lot.
Thank you. We'll have time for one quick question because then for second time, we have to move. So I'm sorry for other people in the queue, just one question, and then we move to next speaker. And of course, you can reach Abdelkader offline and also through the mailing list if you want to share your thoughts, comments, and questions. So just one question from Mohamed.
Hi, thank you, Luca, for interesting talk. I was wondering, when user provides an intent, how and which part of the network actually translates into something that machines can understand or converts into JSON or something like that?
So when the user will introduce the intent, it will be in natural language. So for example, deploy something on our infrastructure in natural language. This is an example. Deploy 5G communication service on the most available parts of the virtualized infrastructure. Then we use AI approach, LLMs, to generate the low-level configurations from this natural language. So we are generating a JSON structure that the users. So we are generating this JSON structure to include some low-level configurations of this requested service. And this is generated by our approach, OSGPT. And then we give this JSON to the OSS, which is our management framework, and the OSS will deploy this on the infrastructure.
Okay, no, thank you. Thank you. I can't see the slide deck somewhere if you can provide it in the mailing list or anywhere.
Yes, it is. I guess you can have it in IETF materials in the agenda.
Yes, you have all materials, yes, of course, in data tracker. So do not hesitate to have a look at it, and of course, contact you. I think there is a nice discussion, but we have to move on. So I will just invite thank you again, Abdelkader. Invite the next speaker.
Thanks a lot.
The next speaker is Yonsei Wai.
Hey, hello everyone. I'm Yunze from Tsinghua University, and I'd like to share our recent updated work of framework and automation levels for AI-assisted network protocol testing. Let's first recall our background. We focus on the problem of network protocol testing, whose task is to test protocol implementations such as switches and routers to ensure the protocol conformance, performance, security, etc. However, traditional network protocol testing methods is mainly labor-intensive. Engineers first need to analyze the protocol sophistication such as RFC documents, design test cases, and convert them into executable artifacts such as the scripts for the tester and the configuration for the device and the test, and then execute the test in the test bed and finally analyze the report. The drawbacks are obvious. It has a very low efficiency with limited coverage. It also struggles to adapt to the rapid evolution of network protocols in the new scenarios, such as the industrial internet satellite networks and some modern DC, data center networks. So we introduce our draft, which contains three main parts. The first part of our draft is a framework of the AI-assisted protocol testing method, which has four submodules. That is protocol formalization, test case generation, and test artifacts generation, and the execution and feedback module. The input of our full framework is the raw RFC document, and the output includes some test cases, tester scripts, duty configurations, and finally the test reports. We also introduce automation maturity levels for the protocol testing. This provides a reference model describing the evolution from the full manual testing methods to the fully autonomous testing systems. We think that this serves as the technology roadmap for the protocol testing automation. Finally, we also provide a concrete and LM-based example for the automated testing. Then I will show our updates in our new version. The first key update in our new version is the framework. We changed the protocol understanding part to protocol formalization in our new version. In version 0, we use protocol understanding, which is a loosely defined extraction process. But we think that this is a very, very important part in the whole test case generation and the whole workflow of the framework. So we emphasize it as a protocol formalization, which is a more rigorous process that can translate the natural language descripted RFC documents into some machine readable structured formats. This helps to promote the test case coverage in the subsequent tests. Steps. So we emphasize this in the figure. It is not included in the last version, in the past version, yes. And we also remove the human intent from the input because we think that human input may happen in every stage until it grew to the fully automated system. And we also make some updates to our LM-based examples. Firstly, we introduce more details of the protocol formalization process. We first make the pre-process to the RFC documents, which divides the RFC into some different types of function modulars. we divide them into two categories: the basic and the logic. The basic function modulus includes some message formats and local data structures, finite machines, etc. These modules themselves can generate some test cases, but they also can serve as the foundation for other logical modulus. And the logical modulus can include some event action rules, algorithms, and error handling, etc. We also capture both the internal and external relationships. For example, the internal relationship is the relationships between some modulus and some sections, which section supports another section in the RFC. And we also capture the external relationships. For example, which RFC updates another RFC or it extends another RFC. Yes. I think this process provides more precise guidance for the LLM and it reduces ambiguity. The second update to our example is that we changed the test case generation modular to test case templates and we decouple the test case templates from the parameters in different steps. We first let LLM to generate a test case template without parameters, and then it can generate either the parameter itself directly, such as the typical values or invited values and the boundary values, or it thinks that the input should enumerate in to improve the coverage, so it can generate some code snippets to generate some test inputs. It can also decide whether to generate some code snippets to calculate the test oracles. You know that some test oracles need to calculate to get the precise value to judge whether the test is passed or not. So I think this method is a hybrid approach that combines both the model-free method and the model-based method, and it's just attempt, I think. And finally, we also update the test code generation modular from a single agent system to multi-agent system. We use a core agent to generate the test code with some sub-agents handle the auxiliary tasks such as the test intent rewriting and bug fixing. Then is the next steps. Our draft is very comprehensive to some extent, so we will discuss. We are also discussing which part is the key part of the draft that was standardization. We will refine these parts with more details in the future. We are also discussing how to evaluate the test cases. This is also a key challenge in the AI assistant framework that based on our investigation, because it can guide our system to produce better test cases with more coverage or something else. So maybe this can collaborate with BMWG, I think. We will also make more industrial collaborations. This ensures that our proposed framework will meet the practical real-world needs in the future. Finally, we sincerely appreciate your valuable comments and feedback to our draft. And thank you very much.
Thank you. Time for questions. There is Xing Zhao.
Yes. Thank you. Thank you for your work. And we all know IETF has so many protocols, so this work is meaningful and useful in practice. But I am just worried that the content in the draft, if they are suitable for standardization. So that's my concern. So I have a little suggestion that maybe you can focus on the part that is suitable for standardization, like the protocol formalization part, like the template, but not the testing method. I don't believe IETF will do some testing method standardization. So,
Okay, thank you.
Okay,
Thank you very much.
thank you.
Just maybe to comment on that, as is presenting in NMRG, So I think if I understand one part of your comments, you'd like to understand what will fit to research, so research group like NMRG, and what could be into the IETF. So I think it's, if I understand well, you would like to see what can fit standardization, so IETF, what will remain here somehow.
Okay, because he mentioned the standardization, so maybe you can consider where to put forward the draft.
Yes, thank you very much. We'll consider your suggestion. Thank you.
Gunchen from Huawei. I think it's a very interesting topic. So my question is that will this cope with the complicated scenarios? You know, the box emerges with multiple protocols involved. So in complicated scenarios, will this cope with multiple protocols?
Thanks for your question. I think it's also a very important scenario. Our current focus is on some more static and single protocol scenario, but we will also extend our work to more dynamic and multi protocols with multiple devices scenarios, more complex scenarios. But I think it's another work maybe. Yeah, thank you.
Okay, thank you very much. Next speaker, please, is Yon. Ah, okay. Okay, so you are?
Natalie.
Okay, so this is Natalie that will present. Thank you.
Good afternoon, everybody. My name is Natalie Roma from Deutsche Telekom. Oh. Okay. I'm from Deutsche Telekom, and I am here to present the draft applicability of MCP for the network management on behalf of the authors team. As a short recap, we presented this draft for the first time in IETF 123 in the NMRG meeting, and we also had a follow-up in the subsequent NMRG interim. We have here the GitHub link with we track the progress of the draft and the corresponding issues. So now, what is this draft about? I think most of us know about NCP, and we're also quite aware about the rapid adoption across both startups and enterprises, mainly for use cases like AI coding assistance, database query, data analysis, and in general to provide AI agents access to tools. So what we're trying to do with our draft is to explore how MCP can be applied in the network management. And we're doing that by addressing different aspects that we list here. First one is the high-level challenges. Second is how MCP can be used for network exposure. The third one is how MCP can be, how MCP discovery could look like, what are the deployment scenarios, and what are the architectural requirements. Since the last version that we presented, we added significant context to the high-level challenges, the deployment scenarios, and the architectural requirements. So I'm going to go through those here. Well, when it comes to adopting NCP for network management, we see challenges in two main areas. The first one is protocol design, and the second are the security considerations. Regarding the protocol design, there are different problems. The first one is the lack of an entire error handling mechanism enforcement. MCP right now has some basic error codes, but they are limited to discovery and invocation, and they are not applied, for example, to an entire lifecycle management. The second problem is that the protocol relies on on server-sent state events. That means it is stateful, and this makes complicated load balancing. And for remote servers, network latency latency and stability can cause problems. And the last one is context handling, because whenever there are large lists of tools available on in one MCP server, or when there are multiple MCP calls, the amount of context and the amount of tokens consumed by this is big, and this can end in degradation of the LLM performance and degradation of the reasoning mechanism, which leads to even more ambiguity and uncertainty. For the second area that was security consideration, of course, we have the different attacks that malicious actors can execute. For example, prompt injection, tool poisoning, tool shadow. We also have the lack of a security performance mechanism that is inherent to the protocol. So far, MCP relies on external implementations for authentication and authorization. And of course, we also need a well-defined identity management that distinct requests from users, from agents, or from sharing systems. The second part, what we added some updates to the draft, were the deployment considerations in the adoption of MCP. We described 4 different deployment scenarios, which are the standalone MCP server to expose APIs, the network controller and network element communication using MCP, network element intercommunication, and how the network controller can consume APIs or data sources from external services also using MCP. Here's our first scenario, which is the standalone MCP server. Here in this scenario, we have a network controller, which has an integrated network management engine with its corresponding MCP client. And we define the MCP server to be deployed standalone on top of the network elements. Now here we have 2 options. Either the MCP server, these network elements are regular, normal network elements, and the MCP server acts as an adapter between the MCP protocol and the standardized network, standardized configuration protocols like netconf. Or these network elements could be also evolved versions that can directly communicate to the MCP client. In our second scenario, we define how the network controller can communicate to the network elements, but the difference with the first scenario is that here we describe the MCP server to be deeply integrated into each network element. That, of course, can consume some computational resources, so it has some drawbacks, but it is a scenario that can be considered. Our third scenario goes a little bit more in the future and considers network elements that already have some intelligent capabilities. So here we foresee agents embedded into the network elements, probably powered by small language models. And inside each network element, there should be an agent and an MCP client and an MCP server that enables the communication between both of them. Of course, this also enables the possibility that a human operator can directly use a natural language to communicate directly with the network element. And last, I think this figure is just self-explanatory, is just how MCP can enable the communication between the network controller and external or third-party management systems. In this scenario, again, we have the MCP client in our network controller and MCP servers exposing third-party tools or data. And the last update was regarding the key architectural requirements. Here we define 3 main key points. The first one is that we believe that we need a function-specific MCP servers. This is to maintain appropriate architecture and a proper performance when the amount of tools is growing. And therefore, we think that the servers should be categorized by network management functions. For example, typical categories can include network log analysis, device configuration management, energy consumption, etc. The second key point that we define in the draft is the secure and scalable architecture. Of course, we need to enforce the strict access controls limiting MCP operations to authorized AI models and to scale efficiently. And finally, we define that MCP implementations should support LLM coordinated automation of real-time diagnosis, fault remediation workflows, and other common management operations to reduce operator workload. That's it. Those are all the updates that we did to the last version of the draft. And now we would like to ask to the audience whether this work is interesting for NMRG and whether this draft is also ready for our group adoption.
Okay, thank you. Yes, we have questions, so please go ahead with this question.
This is Minzhe from Zhonghua Lab. I have two questions regarding the deployment consideration in page 4. Yeah, in your second consideration, you propose to use MCP for the communication between network controller and the network element. So my question is, how do you consider the relationship between MCP and existing protocols like SMP and YAM model? The second question is about your third consideration. You propose to use the MCP for the communication between network elements. But in my understanding, the MCP is used for the agents and the tools or functions communication. What do you consider to use MCP for in this scenario? That's my question. Thank you.
Okay, for the first scenario, maybe I can use this slide. Just if I understood your question, this was how do we see the integration of normal network protocols like YANG and others. So this was something that I mentioned, that here the MCP server can act as an adapter between the MCP protocol and regular configuration protocols like netconf, like YAM models, and so on. So this server will be the translator in a layer above the regular network elements.
Okay, thank you.
Okay, thank you. We have another question. Last question.
Hi, thank you for your presentation. And this is Hao Ran from Digital Lab. And according to your slide, the third page, you list some malicious actors like prompt injection, field pointing, and shadowing as security contents. And I was wondering, is there any network management specific threat model for MCP, or you just plan to define in this field, and rather than only relying on the general large language model security discussion, or just plan to do this? Thank you, and that's my question.
Thank you for the question. So for the moment, I think that the security threats that affect the general MCP protocol, of course, also affect the network management. But as soon as we start experimenting with implementations, of course, I think there is a possibility that there are other specific threats that only apply for the network management. But I think we need some more research for that.
Okay, thank you.
Thank you again. I'm sorry, but we have to stop the question now, and you can continue offline or just after the meeting. So thank you again
for
your presentation. So next speaker is, I think, online, or is here? I think it's online, right?
Yeah, am I audible?
Okay, we just prepare the slides. I will give you the control.
Yeah.
Yes.
So just to confirm, I'm audible, right? Am I audible?
Yeah.
Yes, you are.
We can hear
Perfect.
you.
Yes, yes. Okay, so good afternoon, everyone. So my name is Shailesh. On behalf of the authors and contributors, I'd like to present this work on the applicability of agent to agent to the field of network management, right? So, this work explores how multiple agents or A2A interfaces with the network management, especially in the multi-domain and multi-vendor networks that rely on IETF technologies, right? So what I'll do is, as part of this session, I will go through the A2A concepts and explain why this is important to the network management areas, and also come up, explain our proposal of integrating the YANG-based structured data into the A2A communication, right? Okay, so A2A is basically an open protocol for communication and collaboration between the AI agents, right? So these AI agents exchange something called A2A messages, which each with each other, and that's the single turn of communication between the agents, right? And each A2A message has multiple, one or more parts to it, right? And each part is a container that has the actual content, right? So a part can either contain a text or a binary data or an URL or a structured JSON data, right? So conceptually, an A2A, an agent can send a message that has multiple elements to that, including a natural language description or an artifact that is generated during the processing, or it could also be, a structured data that actually describes the task, right? So as you can see in the image here, so the network operator interfaces with the client agent here, and the client agent then communicates with the remote agents using the A2A messages, and they actually do the network operations, including the configurations, troubleshooting, and the monitoring part, right? So within the telecom domain, there's some work happening at the TM forum on A2AT, right, which is basically extending A2A to the telecom use cases, right? So A2AT is proposing something called the structured prompts for network operations. For example, in this, the example that I've shown in this fault diagnosis task can have structured sections like, task descriptions, target objects, environmental information, constraints, expected outputs, and so on, right? So these structured sections help better, understanding and better interpretation by the multiple agents, right? So that improves the readability perspective and the validation perspective from the agent's point of view. So however, there is still a limitation to that, because while A2A defines how agents talk to each other, it kind of lacks defining standardized semantics for the data exchange between them, right? Most of the A2A messaging is still largely dependent on the natural language descriptions, and not the human or the machine readable forms, right? So that is where we propose, as part of this draft, a YANG-based structured data for agent communication, right? So the whole idea is to integrate the IETF YANG model data as part of the A2A message itself, right? So as we know, the YANG provides a well-defined hierarchical, machine interpretable representation of network data, right? So integrating YANG with the A2A messages brings in several advantages to us. And firstly, it provides a very clear and machine parsable definition for network operations. It also provides seamless integration with the existing ITF technologies, right? For example, RESTconf or NetConf or something like that. And more importantly, it brings in a human machine synergy, because a part of the A2A communication message is, the natural language description, which is good for human readability. And the second part of it is the YANG-based structured data, which is good for the machine readability, right? So that way it brings in very good, human machine synergy into the aspect. So here's one example which I wanted to showcase, which is an A2AT message example for for a network incident model, right? So as you can see, the first part of it is the natural language for the human readability. It says something like, please diagnose a service degeneration incident for optical service A in FAN domain, right? So that's for the human readability part. And the second part of it is actually the YANG based structure data, which explicitly mentions the fields like, what is the incident ID, what are the affected service instances, what is the domain, what is the priority, and things like that, right? So I mean, we have used the network incident Yang model that is defined in the NMOP working group. So this kind of provides the flexibility and the clarity as to what needs to be validated by the machines, what needs to be interpreted by the machines, right? And as you can see in the diagram, the client agent picks up the operator's intent, and then the fault management agent is the one that actually does the fault management operations, right? And it can use the tools and APIs via an MCP server to do so. Right? So this is one of the key updates to this version of the draft, and there are several other updates that went in the 0.2 version of the draft, including the operators operational considerations for integrating A2A into the network management scenario. So what I'd request the working group is to go through the draft, and we very much welcome the feedback and any comments that you may have, right? And I also wanted to check with the chairs if the research group NMRG is interested in a draft like this. So that's all from my side. Thank you.
Thank you. Thank you. We have one question.
Thank you, Chair. Again, Xing from CAICT. One question, and the advantages of A2A communication, maybe they are more flexible, and they can support to communicate with each other through the natural language, and not only the information that defined in Yang model. So if we ask the agents to communicate with each other, which must have the Yang model information, I'm worried. What if we want to interact with each other about the things that are not defined in Yang?
Right. So that's a good question, right? So basically, as part of this draft, there's also a part of the draft that says that each agent exposes something called an agent card, which exposes its capabilities and what are its configurations, what can it do, what it can't do, right? So as part of that, if the agent card says that this particular agent has the capability of parsing Yang or enriching Yang as a structured data, then we delegate that into that agent, right? So not all agents may be capable of that, right? So based on the agent capabilities, we choose to delegate the network operations and functions or the Yang based operations, right, to specific Yang, to specific agents based on their capabilities, right? So that's part of that draft.
Okay, that sounds reasonable. Okay, I will email you if I have any further source. Thank you.
Yes. Yeah.
Thank you for your work.
Yeah,
thank you.
Thank you very much. So you have to also to move to the last presentation. Thank you, Shailesh.
Thank you.
I tried to 5 minutes. Okay, hello everyone. This is John Porjong. I'm editor for intent-based networking use cases draft. The next slide, please. Oh, thank you. So I have updated this draft from Jerome's valuable comment. So I believe I addressed all comments. Okay. So, okay, this one is the difference between version 2, version 3 table of contents. The major the updates are four. The first one is the usage of IBM methodology. So which means methodology, we have IBM construction, how to apply, like intended translation and verification, something like that. So section 3.9. So I made some table. So we have actually 9 use cases. So construction number means from the intended translation, intended verification. So we have 8 steps. So what kind of steps are used for each use case? Second one is the intent classification RFC having intent taxonomy. So I addressed taxonomy. Like left-hand side, we have intent taxonomy, given intent. It consists of the 7 kinds of the intent components, such as intent solution, intent user type, etc. So right side, we have the table, each use case, what kind of intent taxonomy components used. So I analyzed. And the third one is the enhancement of a section. So we try to make all use cases text have the same level. So that is okay. Last one. Okay. So this one. So balanced and consistent explanation among use cases. So especially section 3.2, IBM for guaranteeing service level agreement is quite large text. So I shrink and then try to make consistent with other use cases. So you can see I explained this traffic monitoring system according to the intent life cycle, okay, the system diagram. And then lastly, so enhancement of a practice learning section. So the previously we have practical learning for service function training, SFC. This version, I included a cloud-based security system with the I2 NSF. I2 NSF stands for Interface to Network Security Function. This one is for cloud and the edge security service. So I was the editor for this interfaces, so I applied. So that's your, okay. Oh, okay. Okay, I see. So finally, so we addressed all comments of our the NMRG chairman, German, and we believe this draft is has a good shape. Please read this draft and give us your valuable comment. Hopefully, we can address all your valuable comments by next IETF meeting. And then I would like to ask last poll in IETF the Vienna meeting. Thank you. That's your. Any question, comments?
Thank you. So question, comments?
Also, I sent the email to our group, so please respond to my email.
So thank you very much for receiving my comments, not as chairs, but also as a participant to the group. I really appreciate. And yeah, as you propose, I think the plan you propose is good. So, and yeah, it would be good that if people can give feedback. And so, of course, there will be then, let's say, a kind of formal last call. But before the last call, we would like to also, and I think for the author to have the feedback, so that can really improve the draft if needed before we go for this last call.
Okay, thank you. Appreciate.
Thank you.
Okay, thank you.
So thank you very much to all the presenters. Thank you very much for attending, participating. And this will end the session today. So finally, with 2 minutes in advance. Yeah. So and I hope to see you around, of course, and of course on the Thursday session. Thank you very much, and have a nice evening.